Today's topic is Introduction to Deep Learning and Neural Networks. Okay. So I'm Shailendra Kadre and I'm the convener of this club, AI Club. I'm the convener of AIClub.ai and I have many friends who are supporting me in this venture. So one of them is Uddesh Soman. And so today we will start deep learning. Before that, we had around 6 to 8 classes of machine learning, and machine learning classes we had, and those machine learning classes were more related to the like foundation classes. They were foundation classes. Okay. So I think we are done with that, and the recordings are available on our channel. On a link, I think I shared already. And if not, I'll share once again after this meeting. So I'll see what we'll cover in the deep learning. First is the foundation machine learning course we have already completed. We have taken more than 2 weeks to complete it. Then we have simple artificial neural networks. After that, we'll take up convolution neural network, CNN. Then we'll take recurrent neural network, RNN. Then we have some advanced topics in neural networks. And then there is one more important topic of hyperparameter tuning of neural networks. And then I'll give you one major assignment, and on each of this topic I'm planning to give one assignment so that you do some homework and you make your learning more robust. So I will give you one assignment on ANN, one on CNN, one on RNN, and one on hyperparameter tuning. So like 4 or 5 assignments I'll give, and for every assignment I will give you the model code from where you can copy the code. So even if you don't know much of TensorFlow or Keras, you need not worry, because even I have learned like this way only. I have learned on the job. So you have to see one example, copy that code in another example, similar example. Okay, that's how you have to learn. If you want to learn, TensorFlow traditionally by book or something, it will be very difficult for you. So you learn on the job, on the way you will learn everything. Okay, so that's how we'll proceed. So next, then we go to next slide. Next slide we go. So I'll repeat a bit of machine learning again. So our machine learning problems are mainly divided into 2 categories: classification and regression. So I think regression is nothing but we have covered by whatever we covered with the help of linear regression. It is nothing but predicting your continuous numbers. Classification is we covered with the help of logistic regression. Here the problem is say yes or no. I have credit card transactions, whether they are fraudulent transaction or whether they are good transaction. I have email. So whether email is good or email is spam. So yes or no. So these kind of categories we do in classification type of problems. So these are generally done under supervised machine learning problems. So I want you to write down one thing called something called supervised machine learning problem, which you have to take up as a homework. So take it, supervised machine learning as a one topic for homework. What is it? You have to find out and you have to write it, submit it as a Word document. Supervised machine learning problems. Okay. Then another homework you have to take is what is unsupervised, opposite of supervised. What is unsupervised machine learning problem? That is another topic of homework. Same document you have to submit. You have to do web search for it and then submit it. And the second category which I will tell you is it is nothing but some kind of clustering, like in machine learning classification and regression type of problems. Our target variable is already given to us, like we have y and x, right? Y is target variable, y is target variable and x is dependent variable. So y and x both are given to us, and we use that data set to train the data, train our model. And when we have unseen data on which we have to make a prediction, that time y is not given. So we have to predict y. Okay, so that is nothing but when y is called label or target variable. So when label or target variable is given, that is called supervised learning. And when target variable is not given, and still we have to make some kind of segmentation or something, that time it is called unsupervised learning. So that is on unlabeled data. So like I'll give you example, like there is an example of credit card customers of the bank, or for a telecom company there are customers. So customer they have say around 1 lakh customers list is there. So they have to segment those customers into 3 categories. One is low monthly billing, medium monthly billing, and high monthly billing. So like that, three categories they have to 3 categories they have to segment it. So that kind of segmentation we do with the help of unsupervised learning. So here I have given you an example. So you suppose the left hand side, the blue and red balloons, assume that as a group of customers, all jumbled up. So low category, low price, low monthly volume, medium monthly volume, and high monthly volume, all are jumbled up. And then we have to categorize them. We have to categorize them into low and medium type of monthly billing customers. So applying some kind of unsupervised algorithm, we convert it into say segmentation. So we assume that these red balloons are low billing customers and blue balloons are high billing customers. So we have segregated the data. We have segmented the data. So in that we don't have any label present. Target variable is not present. That's why I have given you an assignment. What is supervised learning and what is unsupervised learning? So you have to discuss with example. Both these things you have to discuss with example in a Word file and submit it. Okay, next week. Then now in the same category we are going classification and regression. Now we are discussing only classification and regression type of problems. We are not dealing with clustering data. We are not dealing with unsupervised problems. So we are dealing with classification and regression type of problems. So in that, one more category is there, that is called neural networks. Okay, that is called neural networks. So you will wonder what is neural network. Actually, whatever I have shown in whatever you are looking at screen, it is nothing but inside your brain. Actually, it is inside your brain. So you have this type of structure inside your brain. So it is a schematic of what is happening inside your brain. So whatever centroid you are seeing, the centers, they are nothing but neurons. You might have heard of neurons. So they are neurons. So there are 1, 2, 3, 4, 5 neurons shown here. And all the neurons are interconnected by veins. Like you see the veins, they are interconnected. So there is a information passing from one neuron to other neuron. So a full network of brain in a human being takes intelligent decisions. Okay, we can learn almost anything under the sun. A human being can learn almost anything under the sun. So it's a very, very complex network of billions of neurons on inside our mind. So copying that kind of that kind of setup is not possible for a human being. For us in computers, it is not possible to exactly copy this kind of setup which is there in our mind. But ultimately, our aim as machine learning engineers, our aim as artificial intelligence is to mimic our brain. Like we want to achieve what is there inside our brain. Using the computers, we want to same thing what our brain is currently doing. But we are nowhere there yet. We are not even anywhere near to it. We are not near to it. Somewhat we are doing some intelligent tasks, but we are not near to what our brain is doing. We have to go longer. Maybe it may take 50 to 100 years more to 100% copy our brain in a computer. It may take more 50 to 100 years to copy our 100% of our brain into a computer. It may take that much time. So you will ask me that you talked about 2 algorithms. One is linear regression, logistic regression. This type of simple algorithms you have talked about. Then why do you need neural networks? What is the need of neural networks? So linear regression also is solving a regression type of problems, and neural networks is also solving regression type of problems. So why do you need neural networks? What is the need of neural networks? So that's what we are going to see in the next couple of slides. See, now I have presented one simple 2 diagrams in front of you. Left is left diagram like left rectangle. you have below some blue dots, and then plus red plus signs are made above that. This one I am telling you, this one. So this one is that, this one diagram. So actually, just a minute, let me draw it. Let me draw with the help of a pen. Okay. So these are blue dots, and these are red ones. Okay. So now these are two classes. Some kind of assume that blue one has good transaction, and assume that red one has a bad transaction, bad credit card transaction, bad transaction and good transaction. All are jumbled up actually. Okay, so our job is to separate which transactions are good and which transactions are fraudulent. That's what we have to separate. Okay, so we make a logistic regression model. So those who didn't attend our first 6 to 7 classes, they need to understand what is a logistic regression, what is linear regression. So they can write this as a homework of themselves. It is not necessary to submit it to me, but you should understand what is logistic regression and what is linear regression. So sit here with a copy and pen and write down whatever I am telling. You need to understand for yourself what is linear regression and what is logistic regression. Okay. So these are two simple algorithms. So logistic regression is a simple algorithm which helps us in separating this kind of yes or no. So once we have applied a logistic regression data to the left hand side rectangle, we got this kind of line. The line which you are looking at here, this kind of line we got. So what is this line? This line is nothing but logistic regression model. This line is logistic regression model. So what it is doing? It is doing a useful task for us. It is separating bad on the upper side and good on the lower side for us. So it is doing some task for us. Bad transactions are getting separated from good transactions. Okay. So this line which is there in the middle, slant line you are looking at, it is nothing but the logistic regression model. Okay. And we are applying it, we are getting this line by applying the machine learning model called logistic regression. It is called decision boundary. Below this, blue dots are all good, and above this, all plus which are red, they are all bad. So it is a decision boundary. It is called decision boundary of logistic regression. So now, what is happening? You listen. What is happening? It is very simple. All above this line, all are bad, and below this line, all are good. Only very simple decision boundary. I will take you to the next slide. Now, what will happen? This side, I have three clusters. One blue cluster here, which is good. Then I have one bad cluster here, which is bad. Blue one, bad, and this is again good. Can I draw a single logistic regression line separating those? Can I draw a single line? Can anybody attempt this question? Can a single line in this case separate good by bad? Can it be done? Anybody wants to attempt this question?
No, sir.
It cannot be done, right? So now, but I am like very stubborn. I still applied logistic regression in this. I still applied logistic regression, and then what I got is this red line which you see here. Here, red line you see here, red line. This is what I got. This is what I got from logistic regression. So logistic regression is totally failing here, you see, right? It is not even able to separate even two clusters. Whatever logistic regression line I got is just near to some junk line near to the origin. It is not useful. So my logistic regression is failing. My logistic regression is failing when I have multiple decision boundaries. When I have multiple decision boundaries, my logistic regression, which is a simple machine learning algorithm, it fails. So what we'll do? We'll go for a more complex algorithm. We go for a more complex algorithm, and we draw these two kind of, and these algorithms which is shown on the right hand side. It gives us two kind of line. This one and this one. One line, and two lines. These two lines I get. Okay. So these are also decision boundaries. But logistic regression, which is a simple model, it cannot give us this kind of decision boundaries. To get this kind of complex decision boundaries, I need a complex model. And what that complex model is? That complex model is nothing but neural network. Neural network or artificial neural network. We call it neural network or artificial neural network. So neural networks are called universal approximators. What is meant by universal approximator? So there is a relationship between y and x. There is a relationship. Y is your target variable and x is independent variable. There is a relationship. Okay. My logistic regression fails. My logistic regression fails. So I apply this kind of model. This kind of model I apply. So it can approximate any kind of relationship between y and x. Whatever is the relationship between y and x, whether it is square, whether it is cube, whether it is a quadratic equation, or whatever is there, whether it is exponential equation, whether equation involves sine or cos, any kind of relationship can be approximated with the help of a neural network. Any kind of relationship between y and x can be approximated with the help of neural network. So we call this neural network as universal function approximators. Universal function approximator. Is it clear to everyone? Is it clear to everyone?
Yes, sir.
Okay. So that's why we need universal function approximator, because we have very problem with very complex decision boundaries. This what I have explained you. I have explained you like they are only straight line boundaries. So I will show you some. I want to show you some complex decision boundaries, which you will wonder. I will just give me a second. I will Google it out. This complex boundaries. So Google God is there for everything. So you see the images, complex decision boundaries. Okay. So now you see this one particular, this kind of boundary which is there in front of you, here. I make it big. So this decision boundary. So like all red ones you assume they are bad transactions, and all blue ones you are assume that it is a good transaction. You see how complex curve it is there to separate them. So neural network can still generate this kind of curve. Neural networks or artificial neural networks can generate this kind of curves to separate good transaction from the bad transaction. Yes or no? So you assume that red is no and plus blue is yes. So how complex the boundary is? Okay. So this kind of curves can also be this kind of complex decision boundaries can also be generated using neural networks. So I'll repeat once again. Any kind of complex decision boundary like this, which I'm showing on the screen, can be generated using the help of neural network. That's why we go for neural networks, and that is why they are called universal function approximator. Okay, so this is clear now. So see, this is again I'm showing what are neural networks. We are going to that. So neural network which is shown on the left hand side is brain. Of course, we cannot copy it. Next 50 to 100 years it will take to fully copy our brain into computer. It will take, but now what we are doing? Right hand side, whatever you are looking at, this figure. So this figure is nothing but our own brain which we are making in the computer. It is called artificial neural network. This is nothing but your whatever this is input layer. This is output layer. And this is hidden layer. This is hidden layer, input layer, and output layer. And of course, whatever I am showing you is one of the simplest neural network. We have now neural network in which we have hundreds of hidden layers like this. There will be one input layer, hundreds of hidden layers, and then we have output layer like that. Okay. So we have very complex neural networks in place. So if you want to approximate a very complex function, very complex relationship between y and x if you want to approximate, then you need multiple hidden layers in between. If you want to approximate simple function, then simple with one or two hidden layer also you can do the job. So depends on how complex the relationship between y and x is. If the relationship is complex, your neural network also will be complex. So this is nothing but this type of diagram is called neural networks. This type of diagram is called neural networks. And you see, all these small ground rounds are nothing but they are called neurons. Neurons. These are neurons. So these are all neurons. So you see, all neurons are interconnected with each other. Okay, they are all interconnected. So there are some initial terminology which I want to introduce you. Input layer, the leftmost layer, output layer, the rightmost layer, and in between whatever layers you have, they are called hidden layers. And all these points which are there, all these nodes which are there in the layer, they are called neurons. So we got introduced to few terms now. Now we go ahead, compare it with your brain again. So this is nothing but, this is your brain. One neuron we are showing. So this is neuron, this is nucleus, this is neuron, and these are all connections, like this connection. So like that, this is our neuron. This circle is our neuron. These are our inputs. These are our inputs to this neuron. And these are our outputs. These are inputs to our neuron. And these are outputs to our neuron. Okay, output to our neuron. In between, what it is doing? In between this neuron, round neuron, is doing some function. First is sigma. Sigma means it is integrating all the inputs. All the input which are getting, it is integrated with the help of sigma. Okay, it is integrating all the inputs. Integrating all the inputs. Once all the inputs are getting integrated, we apply a function on it. We will go in detail of everything. You don't worry. We apply some mathematical function on integrated inputs, and that gives us our output. That gives us our output. So this is simple concept of neural network, or this is a simple concept of a neuron. What neuron does? It does summation. Summation of what? Summation of inputs. And f is what? F is a function which we apply on the integrated data, or summation. In this summation, we apply a function, and whatever is the output of that function is our output. Now we'll understand. So this is the basic structure of our basic mechanism of our. This is the basic mechanism of our neuron. Okay. Now we go next. Same thing. So we have inputs. First of all, inputs. I will tell you what input is. With every input point, we have weights associated with. Weights associated with. So x0 w0, x1 w1, x2 w2. Then we have activation function which we told f, and then we have output. I'll tell you now how it is. So again, same thing. And who was the inventor of a very basic neuron? He was the guy called Rosenblatt. Rosenblatt in 1957. He invented the most basic. Neuron, which is called perceptron. Perceptron is the most basic neuron which was invented by Rosenblatt as back in 1957. Okay, so what is that perceptron truss? That is the very basic unit of any neural network. What it does. So first of all, let us understand whatever I have already explained. So x1, x2 up to x1, x2, x3 are inputs. W1, W2, and W3 are associated weights. And then we do a summation W and Xn. So here x varies from n is equal to 0 to 2. N is equal to 0, n is equal to 1, n is equal to 3. Okay, so like 3 inputs, x1 W1 plus x2 W2 plus x3 W3. Like that we have a summation. And on that summation, we are applying a function here like this. Here, function we are applying. And on that summation, we add a bias. We always add a bias. We always add a bias to summation. And on that, we applied a activation function A. Okay, so that is our output. Don't worry by all these terms. This will all get greatly simplified. You have to just understand the basic mathematical notation. That's why I'm explaining this. So again, same thing. X1, X2, up to Xn are your inputs. All W's are weights. Then we first do summation. Xi, Yi, we do summation. Then after that summation, we apply a transfer function. and then transfer function is nothing but it gives the output. So what is now, we'll see what is output. So what our basic perceptron does, which Rosenblatt invented in 1957, what it does, you look at this particular diagram. It is called a step function. It is called a step function. Step function. It is called a step function. What is a step function? Now, does anybody wants to attempt it? Anybody with electronics background or something? They want to tell, explain what is a step function? Anybody with electronics background or computer background? What is a step function? Anyone?
So as shown here, it is just a step. Like unit step function will have a unit value throughout, and it will change from 0 to 1. There is a step involved.
But can you explain more clearly? Like, I want a better explanation. You are right only, but I want a better explanation. Can anybody attempt? Any of the seniors, please? What is step function? With electronics background, this you must have learned in your electronics, na? Very basics to electronics. See, I will explain it. This line which is there here, this line, this is less than 0, like less than 0. So for any value less than 0, the output is 0. Output is 0. Any value 0, any value greater than 0, the output is 1. That is called step function. See, it is shown here, right? For any value of x less than 0, the value of y is 0. And for any value positive, the value of y is positive. That is what is step function. Very basic. Understood? Is this understood by everybody?
Yes, sir.
Can anybody explain once more what I have explained?
So step function basically has two values, output 0 and 1,
Okay.
and they are pairwise disjoint.
Okay. But for negative value, any negative value of x, the value of y is 0. And for any positive value of x, value of y is 1. Is that correct for step function?
Need not be.
It is correct, right? Who is speaking? Ravi, yeah?
Ravi, yeah.
Yeah, see here, step function. If x is negative, y is 0. If x is positive, y is 1. Clearly you can see with the graph, right? The step function is clearly showing you that for anything less than 0, we have value of y as 0. For x anything greater than 0, we have value of y as 1. It is very clearly seen from this diagram which is in front of you, right?
Yeah, this diagram shows that.
I think one way to understand this is it's a function which will give you two values, kind
Correct.
of true or false. So
Yes.
depending on some level which is chosen, you will say anything less than that value is false or 0, and anything higher than that by whatever amount is true.
Yeah, so here I have chosen that value as 0. Okay.
Right.
Less than 0 means value of function will be 0. Greater than 0, that means value of function will be 1. Is that correct? Who was this? Can you tell your name, please?
Sorry, I'm Yogesh.
Okay. So this is how the step function is. And this is what Rosenblatt invented. Rosenblatt's perceptron gave only two outputs, either 0 or 1. Okay. So see, here again I am showing once again, whatever input, you see this diagram. Whatever is input, x1, x2 up to xn, apply weights to it, do the summation, and then this output will always be a fixed function. That is what Rosenblatt's perceptron was. It was a ridiculously simple machine, ridiculously simple thing, and then Rosenblatt claimed that it can do some complex function as our brain does. So people like laughed at him. Such a simple thing which has only two values, 0 and 1, how it can mimic our brain. So he proved it. So how he proved it, I'll explain you that. So I'll explain you that. here. See, now here a bit of your electron, bit of your AND OR gate and all is involved. So now you go back to your engineering days, or the guys, mechanical guys need to understand it. See, AND gate. What is the AND gate? A and B are two inputs to the AND gate, and AB is the output. When value of A is 0 and value of B is 0, the output is 0. If value of A is 0 and B is 1, then still output is 0. If value of A is 1 and B is 0, still output is 0. Value of A is 1, B is 1, then only output is 1. AND gate. Okay. So if any of A and B is 0, the output is 0. If both are 1, then only output is 1. Is this understood? I want to explain how this kind of AND gate, this kind of AND gate can be done using a simple perceptron. I want to demonstrate that. So is this AND gate understood by everyone? If any of A and B is 0, output is 0. If both A and B are 1, then only output is 1. That is called AND gate. Is this understood? Ashwini?
Yes, sir.
Any of the seniors not understood?
This is understood, sir.
Understood? No, very simple. A and B I am giving as input. My output is AB. So AB means what? AB is nothing but a product of A and B. So if any of A and B will be 0, product will be 0. And if both A and B are 1, then product will be 1. So it is a simple AND gate. So now we have to see how we can mimic it with the help of a perceptron. Rosenblatt actually told, he claimed that I can do some complex job using perceptron. So this is also one of the a bit complex job. So people wanted to see how it can be done using a perceptron. Okay, so now you do what you do. You initialize. You assume that A and B. You assume that this A and B. Okay, so I will make it here. So assume that A is x1, A is x1, and B is x2, x1, x2. A is x1, B is x2. So weight associated with A x1 is W1. Weight associated with B is W2. So we have equation like this: W1 x1 plus W2 x2 plus B bias plus B bias. Okay. So we have this equation, summation equation. We do summation first, right? So W1 x1 plus W2 x2 plus B is nothing but the summation of our inputs. X1 and x2 are our inputs. W and W2 are weights associated with, and B is the bias which we add actually. There is a bias term which we add actually. Okay. So is this understood that this is our summation of our input? Is this understood by everybody? Is this understood? Actually understood?
Yes, sir.
Himanshu understood?
Yes, sir.
Shailesh?
Yes, it is
very simple. Na? So now what I am doing, I can initialize these weights first, right? I always initialize the weight. So I am keeping W1 as 1, W2 as W1 and W2 both I am keeping as 1, and bias I am keeping as -1. So listen once again. W1 and W2 I am keeping as 1, and bias as -1. So my equation becomes this: W1 into 1. X1 into W1, X2 into W2 -1. This becomes my equation. Correct. Now let us see. This is my equation. Okay. Now see my first row. My first row, both X1 and X2, AB means X1 and X2, both A and B are 0. So put in this equation both A and B are 0. A and B is 0. What will be the output? -1. Output will be negative. Right? So when both A and B are 0, this equation gives me a negative number. And what my perceptron, my Rosenblatt perceptron said, if anything is negative, if function's value is negative, I'll take it as 0. So we'll take it as 0. Understood this? See, x1, first row you see, first row is what? X1 also 0, x2 also 0. X1 also 0, x2 also 0. So this is our function actually, x1 w1 plus x2 w2 minus 1. That is our simple function. I keep x1 as 0, x2 also as 0. I'm getting value as minus 1. So what my Rosenblatt equation is telling, function is telling, it is a safe function. I'm getting function value, the function which is y. The value of y is coming as negative. Value of y is coming as negative. So anything when it is negative, I take it as 0 because it is a safe function. So it is the first row is satisfied. Output is 0. Okay. Then second row you take. Second row x1 as 0 and x2 as 1. x1 as 0 and x2 as 1. So x1 as 0. So again we are getting minus 1. So value of y we are again getting as 0. Okay. So there is a value of y we are getting as 0. So the value of y is 0. So our function value will be 1. Anything for 0 and greater than 0, our value function is 1. So that also y we are getting as 0. So this then also it is satisfied. Third, x1 as 1. Third, x1 as 1 and x2 as third one is x1 as third one is what? Third one is x1 as 1 and x2 as 0. So third one, row 2. Where is row 3?
Then it will be something similar as row 2.
Yeah, it will be similar. So it will be similar for row 1 and 2 and 3. So when both are 1 and 1, x1 and 1 and x2 as 1, then what I get? My output is 1. So my simple perceptrons are satisfying my AND gate, right? I can easily make an AND gate using that. Is it understood by everybody? A simple AND gate we have constructed using perceptrons. Okay, a simple perceptron we have used and we have constructed a AND gate. Just by initializing just by properly initializing the weight. W1 as 1 and W2 as minus 1. W1, W2 as 1 and bias as minus 1. So is this understood by everyone? Simple equation. I'll share this link anyway with you.
Sir, bias, how it is a minus 1, sir?
Madam, bias is minus 1 because we have just selected it actually.
Oh.
We have selected as minus W1, W2 also 1. We have selected. This value we have chosen. And when we do a neural network, our job is to find out W weights, the weights and bias. That is what is our job. When we train a neural network, our job is to find the proper value of W1, W2 or whatever weights we have and whatever bias we have. Okay, so that is our job. Understood now? So right now we are assuming the value W1, W2 as 1 and bias as minus 1. We are taking these values just to demonstrate the working of a AND gate. Understood? Is this understood, Shrutika madam, Shalini madam, Malini madam?
Yes, sir. Yes, sir. That's true.
See, if
Shailaja, so
Yeah.
basically W1, W2 and bias, you can choose any random numbers. Initially, we take any values and then there is this concept of back propagation and loss function computation. We try to minimize the loss. Shailendra sir will cover that later, where the weights will be getting adjusted accordingly. So, but for the initial case, we have taken the values as 1 and minus 1.
actually I was little bit row number 1 is okay.
Shailendra sir, you are correct, sir. It's okay. We understood, sir. Shailendra, row number 2 and row number 3 are the same case. Row number 4, it is 1 basically. So the activation function here is basically any value greater than 0 is treated as 1 and any value less than or equal to 0 is treated as 0.
No, but what I am confused a bit here is because if you see the PPT, even if y is 0, even if x is 0, the value of y is 1. Understood? No? Even if x is 0, the value of y is 1. So anything x equal to 0 or greater than 0, y is 1. Now here, what I am getting is here, I am a bit confused here because in the row number two, how much will the value? The row number two, the value of output variable will be 0.
Correct.
Output variable will be 0. So value of y is 0.
Correct.
So, no, sorry, output function is 0. So we will take it as 1.
1. Okay.
But that is not the case here, na? That is not the case here. It should be 0 only. Right? Output should be 0 only. So according to our thing, if value of function comes as 0, we should take it as 1. But our end gate says it should be 0. That's why I'm a bit confused here in row number 2 and 3.
Maybe the bias should be -2. That
No,
is-
no, not like that. It is some other concept actually. Got it correct.
Sir,
Yeah.
so step function says that the value at 0 is 0. Just above 0, it will be 1. Like impulse function. Value, step function doesn't say that the value at 0 is 1.
Okay. So I take that. If value at 0, then the value of function is 0, then also we take it 0. So row 2 and 3 are computed like that. Value of function is coming at 0, so we are taking it as 0. And for row number 4, it is coming as 1. So we are taking it as a 1. 2 minus 1 is 1. So it is perfect 1. Okay. For row number 1, it is coming as negative. So negative will take again as 0. So all the 4 cases are satisfied. Okay. So this is what like what I want to show more here is here he has simulated all the gates. You see, OR gate also simulated similar way. Then OR gate and then NOT gate also simulated with the help of perceptrons. Then you see NOR gate also simulated. So all lot of things he has simulated with the help of perceptrons. Only thing is, see here only thing which is varying is weights and biases. So weights and biases for NOR gate, N-AND gate, let us see N-AND gate. N-AND gate, I'm not going into detail of it, but N-AND gate, what, see W1 and W2, it has taken 1 only. And again he has taken biases -1, same thing. So it is same case as I want to take a different case. So I want to see where or NR what he has taken. So NR is something Boolean representation. So okay, so something I think we need to look into a little bit more detail. But I'm not going into much detail. I share with this article with you, so you can have a look. So he has simulated a lot of gates with the help of simple perceptrons. Okay, so the meaning to say that is simple step function. A simple step function, using a simple step function, we can do many complex jobs. Okay, so we can do many complex jobs using a step function. Then weights and bias is always computed at 1 and -1 only. Then how he has done the computation? OR gate also. Okay, we'll compute one more OR gate. Okay, let us see OR gate. So OR means any of A and B is 1, then it is 1. Okay, so both 0 means both A and B are 0 means output is 0. A or B, B is 1, then 1. A is 1, then it is 1, and both are 1, then also it is 1. So let us see how he has computed it with the help of perceptron. So initial equation is same thing. W and W2 are initialized to 1 and B is initialized to -1. So equation remains the same. Passing the first row, x1 equal to 0 and x2 equal to 0. So it is -1. So x1 equal to 0 and x2 equal to 0 means OR gate says 0. So we are also getting here 0. Let us see the next. Row 2, x1 equal to 0 and x2 equal to 1. We get 1 -1, 0. Okay. So from the perceptron rule, if Wx plus B is less than 0, then Y is equal to 0. Therefore, row is correct. So if we want values that will make x1 is equal to 0 and x2 equal to 1, give y equal to 1, we can change w2 to 2. Okay, so he changed the weight. See, so here equation what he has done, w2 he has changed to 2, w2 he has changed to 2, so it is x1 plus 2 w2 minus 1, x1 plus 2 w2 minus 1. So then if you keep in this equation, then properly it will come. See here, 2 w2 to 0, we get weight equal to 2, then we get 2 plus 0 minus 1, same thing. So he has changed the weight actually. He has changed the weight, that's what I wanted. Now same thing. He has done it for, same thing he has done for both, all rows are satisfied. If we take one of the weights as 2, okay. One time he has taken W2 as 2 and one time he has taken W1 as 2 to satisfy the OR gate. Okay. And then one time he has taken both as 2 to satisfy the OR gate. So for all the three, simply by changing the weights and biases, we can simulate whatever gate we want. Actually, I never wanted to go into detail of this, but just for the sake of confusion, I just went into a bit detail. But just if you read it, if you read it a bit carefully, just by changing the weights and biases, he is simulating any gate. That's what is the message I want to convey here. Okay. So then we go next, and next we go, and that's the for perceptron for complex tasks. This we have seen already. So today's conclusion: a perceptron is the simplest possible neural network. Using the right combination of perceptrons, we can simulate relatedly complex function like AND gate or a OR gate. So that is what I wanted to convey with the help of